Hi everybody, I'm Qiaopeng Li from Virginia Tech, and the project I will present today is stabilizing offshore floating wind platform using dual functional wave energy converter. From the 2018 Offshore Wind Technologies Market Report by NREL, a record capacity of 5,652 megawatts new offshore wind was commissioned globally in 2018. The global offshore wind installed capacity has grown to a total of 22,592 megawatts from 176 operating projects by the end of 2018. The NREL database shows that the 94.4% of projects in the pipeline plan adopts semi-submersible structures. The semi-submersible platform has a shallow draft and a low cost for installation and maintenance. There are four prevailing types of mooring platforms for offshore wind turbines: barge, semi-submersible, spar, and tension leg platform, TLP in short. Among these four types, TLP has the best stability performance but the highest cost. It is widely used on offshore oil drilling platforms. Compared to barge and spar, semi-submersible platform has better stability and lower cost, making it the obvious choice for most ongoing projects. To enhance stability performance of semi-submersible platforms, different types of tuned mass dampers have been proposed. Liquid-tuned mass dampers use eternal liquid mass motions to counter the oscillating motion of the platform caused by wave and wind. However, this requires additional volume and material for the platform structure, causing unacceptable cost increase. In this project, we propose a compact mechanical tuned inertia damper, using rotational moment of inertia of compact mechanical components to provide counteracting mass to stabilize the turbines. This will result in a compact design ready to be integrated into existing systems, a limited cost increase, and additional electricity generation from the stabilization process. The goal of the project is to develop a reliable and economic semi-submersible stabilizing platform for offshore wind turbines. As shown in the figure, when the turbine is moving in heave motion, the inertial components in the pontoons will move in the same direction to provide counterforce. When the turbine is moving in pitch or roll motion, the inertial components in the pontoons will move in the opposite direction to provide a counter moment. The major deliveries of this project are a novel concept design for enhancing semi-submersible platforms, its lab validation, and a scaled prototype test. The advantages of the proposed technology are twofold. First, it can reduce the vibration of semi-submersible platform, such as pitch motion, by 50% in optimal conditions. Second, it can reduce nearly 30% cost in offshore wind turbine development, with a limited cost for the mechanical components, a large volume reduction for the platform, and additional electricity generation. Mechanical motion rectifier, in short MMR, will be adopted as the tuned inertial component. MMR can transfer the bidirectional linear motion of a mass into the unidirectional rotation motion of a generator and flywheel. MMR has 80% energy conversion efficiency and a broader energy generation bandwidth compared to linear power takeoff systems. MMR has been applied to many wave energy converters from Virginia Tech, and its merits have been validated through simulation and third-party tests at NREL. The timeline of the project is listed here. In the first 2 months, we finished the market research. For March and April, we are supposed to finish the platform modeling part, and we are right on track. In May, we will integrate an MMR model with the platform model and perform optimization. In August, we will finish the entire modeling work. In October, we will finish the design work, and in December, we will test the scaled prototype. The actual parameters for this project are still under negotiation at this point. So we built our modeling work based on the dimensions of the OC4 model from Unreal report. In the red box is the platform part we have finished the modeling of. In the green box is its boundary element model for calculation of hydrodynamic parameters. 3 mooring lines are attached to the platform 120 degrees from one another. 2 assumptions are made for the following simulation results. First, we assume that the platform is a rigid body, and the trusses have a trivial influence on the hydrodynamics of the platform. That is to say, the hydrodynamic parameters are calculated based on 3 large pontoons and the central column. Second, the moorings are treated as large stiffness springs. These figures show the motion of OC4 platform with or without TMDs. The wave condition is regular wave, 3 meters wave height, 6 seconds wave period. The first row shows the key row and pitch displacement without using TMD. Since the structure is symmetric with respect to the wave direction, the row motion is almost zero. The pitch motion is also very small. The heave motion amplitude is 0.07 meters. The second row is the heave row and pitch displacement with TMD. The total TMD mass is 2% of the structure mass. The heave amplitude has dropped to 0.05 meters, a 28% reduction. From the third row, the 3 TMD masses have the same motion history and amplitude, indicating that the TMD subsystem is actually countering the heave motion of the platform. Further, we present the 6 degree of freedom simulation results. The mooring line parameters are from the Unreal OC4 report. Model analysis shows the 6 modes of the entire system, considering moorings. The model shapes represent the motion patterns of the system. Surge, sway, and yaw motions have large natural periods, thus are less excited by the wind and wave. Heave, pitch, and roll motions are more likely to be excited. That's why for the 3 degree of freedom model, we consider these 3 motions. However, in the following results, it will be shown that since the wave excitation in the surge direction is huge, the surge motion of the entire system is indeed negligible. This page shows the motion of the platform under 10 seconds 5 meters regular wave excitation. The red lines are the moorings. The red dots in the right subfigures are synchronized with the 3D plots on the left. Again, since the system is symmetric with respect to the incident wave direction, sway, roll, and yaw motions are small, while the surge and heave motions are large. This page shows the motion of the platform under 10 seconds 5 meters irregular wave excitation. The total cost for this project would be $80K. The technology readiness level is between level 3 and 4. The outcomes of the project include the modeling, design, and prototype demonstration of the dual functional wave energy converter for 5 MW offshore wind platforms.